One of the big ideas that we've been dealing with in this section of the course is superposition. That's just a sophisticated way of saying add them up, okay? When I have two pulses that are coming towards each other on a spring or a string or a rope, they don't bounce off of each other like a solid object would. They pass right through each other. And as they pass through each other, what the string or spring or rope looks like is the sum of the two pulses. Now, I acknowledge here publicly that we cannot make a pulse that looks like that, with that sharp kink there. We cannot make a pulse that looks like this on a string or a spring or a rope. However, when you're trying to grade one of these problems and you use real pulses that are all swooshy and kind of smeared out, you don't know whether they've got the right idea or the wrong idea. So I apologize to you, but we're going to use these type of idealized pulses just to make it more clear what's going on. Now, once they overlap, I add them up. Now, over here, all I've got is green. And so that's what the spring or string will look like. But right here, if I call that 1 unit up, I've got 1 unit of red up and 1 unit of green up. And so that's going to give me a total of 2 up. Now if I look over here, I've got 1 unit of green and only a half unit of red. And so that's going to give me 1.5 units. And then it's all red. Now, if I could have these idealized pulses with the kinks, that's what the string or spring or rope would look like at that moment in time. Okay? That's superposition. And then, as they pass further through each other, we just keep on doing that. Now, I would have 1 unit of red and 1 unit of green here, so that would be 2 units. Here, I would have just 1 unit of green. And so that would be 1 unit, and that's what it would look like. And then when they were passing through each other, almost through each other, over here it would be all red. And then here I would have 1 unit of green and a half unit of red, so that would go up to 1.5. And then right here it becomes all green again. And so it has to come down here and become green. And that's what it would look like. And then they would pass through each other, strangers in the night. It's almost Valentine's Day. Just trying to do my part to get you in the mood. Okay? Are there questions on superposition? Add them up.
Can you go back a few slides? Yeah, so like where the red and the green intersect. Why did that point, why is the point right where they intersect? Shouldn't it be that point? Should that point be higher? That point be 1.5 units? Or
it's kind of tricky. If you look to the left, just to the left of that tick mark, you just got the red. Mm-hmm. If I look just to the right of that tick mark, I've got some red and twice as much green. And so right at that place, I have to go from just red to both. And that's why I go up to the 1.5. But you're right, it happens just to the right of that tick mark. Okay?
Okay. So you just want us to go like unit by unit.
1 unit of green and this is still up a half unit there. And then let's take it right here. I'm being sloppy. If I do it right here, I've got a 1/4 unit of red and 1 unit of green, and that's going to give me 1 1/4 there. So right here, that would be 1 1/4. And then here I've got 0 of red and 1 of green. So I've got the 1.
Okay.
Okay? Okay. Let's look at this handout. Did anyone forget to bring their handout today?
Today, etc. I broke my liver's going to shut I talked to Sarah. I asked her, well, what is this with I made it posting it for it. I had my last I'm out. I made a 90-day.
It's not worth cramming in if you're going to be sacrificing your understanding for time.
Yeah, exactly. And I had to read all of it down.
Okay. We finished the first part of this last day. Remember, a single pulse, we call it the incident pulse, came in to the boundary and split. We can think of this picture as being a family portrait. These two are twins. They were both born at midnight right there at that boundary. And they scurried apart. Now one of those is the transmitted pulse. It's the part of the original that keeps on going into the new medium. Part of it, one of those pulses, is the reflected pulse, the part of the original that bounced back. Okay? It's split into two. Now, those two are moving away from each other. They both started right here, and when I took the picture, that one got further away. So that pulse on the left is on the fast spring. We're told in this problem that one of the springs is made of steel and one is made of brass. Now that's not particularly important. The next part is, we're told that the linear mass density of the steel spring is greater than for the brass spring. Now remember, the speed of pulses, the transverse pulse speed, depends on the tension, and it also depends on the mass density. That mass density is just how much mass there is per meter. Now, if these two springs are pulling on each other, by Newton's third law, the tension has to be the same in both. And so that means whichever one has the greater mass density is going to be the slower spring. So the fatty spring, the heavy spring, is the slow spring. So we can say that the slow one on the right is the steel. Now, the question that really is challenging is which is the reflected pulse and which is the transmitted pulse. Now, some of you have already figured out a shortcut for answering this question. And I'm going to talk about that shortcut in just a moment. But first I'd like to present another possible approach. This blue pulse here is either the reflected pulse or the transmitted pulse. There's only two possible right answers. Two possible answers, one of which is right. When we have a problem that only has two possible answers, we guess and check. So let's do that. Let's guess and check. I guess that the original pulse came in on the light spring and that this is the reflected pulse. That's my guess. Let's check. If it came in on the light spring, would it come in like this or would it come in like that? Like that, okay? It would have to be like that because the leading edge is always going to be the leading edge, okay? So this part that's shallow is leading the charge. And so as they move away, the shallow part is what's leading the charge. Now, when it comes into that boundary from the light side, is it like hitting a free end or a fixed end? A fixed end. And so that's going to cause the reflected pulse to invert. Well, that's not what we see. We see something on the top. Well, maybe it came in like that. If it came in like that and inverted, now I'd get the right reflected pulse. Anyone see a problem?
Transmitted pulse.
Yeah, now the transmitted pulse is going to look like that. The transmitted pulse always every stinking time is on the same side as the incident pulse. Okay? And so that is not going to work. Now, there were two possibilities. I guessed wrong. But as soon as I figured out that I guessed wrong, I know the right answer. The right answer is it had to come in on the other side. And now, when it comes in from the heavy side, it's hitting a free end, and that means that the reflection is going to stay on the same side. It will not be inverted. The transmitted will always stay on the same side, and so this works. Now, that's the long way to do it. The quick way to do it is to say, hey, the transmitted pulse never gets inverted. The reflected pulse sometimes does, sometimes doesn't. If the original came in on the light side and hit the heavy side, it gets inverted, like a fixed end. If it comes in the other way, it doesn't. So what I look for is, are my two twins, my pulses, the transmitted and the reflected pulse, on the same side or opposite side? If they're on the same side, both up or both down, I know the reflected pulse did not get inverted. That means I had to have come in and hit a free end, which means I had to have come in on the heavy side. If those pulses are opposite each other, if one is up and one is down, then the reflected pulse must have been inverted, which means I hit a fixed end, which means I had to come in on the light side or the fast side, either way you want to think of it. See if your neighbor understands that reasoning, please.
Make perfect sense. Now if I can hold on to that for a couple
Okay. Are there questions on these types of problems? Hey, just for fun, let's look at that problem that you turned in. You have a system with a slow spring attached to a fast spring, and two pulses are created right at noon. right at high noon, and they're sent towards each other. Now, a little bit after noon, let's say 20 seconds after noon, this pulse has gotten down to here. So this would be noon. This would be noon plus 20 seconds. So now, what I find is that that pulse on the left, I'm sorry, that spring on the left is just flat. But if I followed this pulse, I know that it should be right here. But it's not. The spring is flat. Now you'll notice that this incident pulse, pulse A incident, it has not yet reached the boundary. It is not yet split. But the other pulse, pulse B, is on the fast side. So it's already had time to get to the boundary and split in two. Now the only way that I can get this pulse A canceled is if the transmitted part of B actually zeroes it out. Okay, so that would be going this way. It would be pulse B transmitted. Now, in order to get a transmitted pulse that looks like that, I'm going to have to send an incident pulse that looks like that, where it's got a wider length because this is going to shrink when it gets over there.
Is your leading edge supposed to be for the transmitted to the? I mean, I don't know.
I didn't say that the two pulses had to have the same leading edge. So this pulse has a leading edge that's steep, and this one has a leading edge that is shallow. And I do that because when they overlap, they're passing through each other. And I want this piece to cancel that piece, and this piece to cancel that piece, and that piece to cancel that. So they have to be the mirror image of each other. Now, if this incident pulse B has already split, well, it came in and hit free end or fixed end? This one here, when it comes in and hits right here, this is the heavy slow. It's like hitting what kind of boundary? Fixed, okay? And so it's going to invert, and now it's going to look like that, where this length is still L, because it's on the same spring, and this is now going that way, and this would be B reflected. Now, at this time, there's only one A pulse, because it hasn't reached the boundary and split. But there's two B pulses, because it's already hit the boundary and split. See if your neighbor understands that problem, and then be grateful that it's not going to be on your exam. The reflected is always they're on the same spring, but with a lighter but you can't always see okay. While we're talking about these homework problems, let's talk about the one you voted off the island. You have this steep pulse, and then you have this kind of spread out pulse, and they meet a boundary, and in this case, this is the fast over here, and the slow is over here. Now the first part of this, if this is pulse 1 and this is pulse 2, the first part of this asks about the speed of these two pulses. And remember, the speed is given by that formula up there, the tension over the mass density square root. They're on the same spring with the same mass density, so they have the same speed. So if this is 3 meters per second, this would be 3 meters per second. And when this was on an exam years ago, everyone got that right. It was the next part that people got wrong. If I put a piece of yarn there, call it A, and a piece of yarn there, call it B, which of those pieces of yarn will be moving fastest? And there, what people said was, hey, you can't fool me, Greg. They're on the same spring. Everything moves the same speed. Same. That's wrong. Everything's moving the same speed to the right. But remember, these pulses move through the spring by little pieces of the spring getting out of the way. The pieces of the spring, we're identifying that by yarn, has to move perpendicular to the motion of the pulse. So they have to move up or down. Now let's answer this question by considering another two set of pieces of yarn. We'll call this one C and this one D. Now, this piece of yarn at C has to move all the way up to let the pulse pass and all the way down in the time it takes for this pulse to go that far. Okay, it's got to get out of the way and then come back to equilibrium. This piece of yarn at D has to come all the way down and all the way up, but it has to do that in the time that this pulse travels that far. So that means that this piece C has to go yip yip to get out of the way quickly, because that's going to pass through quickly. This one just has, it's moving slowly. Now another way to argue this, if we go back to the original pieces of string, is to wait 1/10 of a second. And that's going to see that these pulses have moved to the right a little bit. Now in order to stay on the spring, the yarn at A has to go all the way up here. The yarn at B only has to go to there. So that means that the piece of yarn at A is traveling faster when we took this picture than this piece of yarn at B. And that's the part that people had trouble with. Now if we draw what happens after both pulses have hit the boundary and split, the reflected pulse, because we're hitting a fixed end, is it. And so now we would have this pulse leading the charge, because it was leading the charge before, and then we'd have this pulse, and so if this is L, and this is little l, this would be L, and this would be little l. Now in the slow, the one that transmits into the slow, I would have things shortened up and closer to the boundary. And these would be both going that way, like that. Okay, how are we feeling about that homework? Good, yes sir.
Would the waves on the transmitted side be further apart?
When it transmits, these things get shorter, and these things get shorter, and everything gets closer together. So if this would probably be longer than I drew it, but it definitely has to be shorter than what it was. Does that answer your question? Yes?
Just so you know, a lot of people I helped with the homework on were confused by that wave being number one and the other one being number two.
I know, because number 2 is what hits the boundary first. And when the problem was written for an exam, it was on the left, and being raised in this culture where we go left to right, it would be a much better problem if it were reversed. Thank you. And when we get to the published version, we should switch it. Thank you. Okay. I promised you, and I will keep that promise, that there will be a simple harmonic motion problem that involves energy. And these problems are really, really ugly if we do it vertically with the block going up and down. And so I also promised you that it would be horizontal on a frictionless table. And so that's this problem here. A 4-kilogram block is fastened to a spring. The spring constant is 200 newtons for each meter. It's oscillating back and forth horizontally, frictionless table. The amplitude is 0.3 meters. We're asked, what is the block speed when it is 0.1 meters from equilibrium? With your neighbor, see if you can figure that out.
No. Just looks kind of.
You could.
Okay. Let's draw a picture so we're not doing a wall here.
Now remember, I taught you that these problems, the first step is always to find the total energy. Now sometimes that'll be part A. Please find total energy. It's worth 3 points. But even if it's not part A, that's the first step, each and every time. Now, you know that there's 3 formulas for that total energy. Not really, there's only one formula, but there are special cases of that one formula. The general case has energy in the motion of the block, kinetic energy, and in the stretch or compression of the spring, potential energy. But there are special cases when none of the energy is in the block and it's all in the spring. That's at the turnaround, because you've got to stop to turn around. And if V is equal to 0, you don't have any kinetic energy. When you turn around, the stretch or compression of the spring is the biggest it's ever going to get. And so we call that the amplitude. Okay? Now there's the other special case where there's no energy in the spring. Well, that's when the spring is neither stretched nor compressed, when delta S is 0. Now remember, delta S is how far the block is away from equilibrium. Equilibrium is where the spring is just the same length it was when it came out of the box from the factory. It's not stretched, it's not compressed. Now at that location, at equilibrium, the block is going the fastest it's ever going to go. Okay, and so we have this formula here. Now, because of time constraints, we're going to work this problem together. The first step is to find that total energy, come hook or by crook. Whichever equation is going to work for you. Now here they tell us K and they tell us A, so I can use that second equation, and I can say that E total is going to be 1/2 times 200 newtons per meter times 0.3 squared. 1/2 of 200 is 100, 0.3 squared is 0.09, and so that is going to give me 9 joules. Okay?
There's 9. 9.
I'm sorry, is it 9?
No.
9 times.
No.
Okay. Now, if I want to know how fast that block is moving, when it's 0.1 meters, 10 centimeters away from equilibrium, I have to use this top equation. Why? Because I'm not at equilibrium, I'm 20 centimeters away. And I'm not at the turnaround point, because that's at 30 centimeters away. I have to use the general case. So I go up here and I say 9 joules is equal to 1/2 times the mass times V, that's what I'm looking for, squared, plus 1/2 times K, that's a 200, times 0.1 squared. Don't forget to square these things. Yes? Joseph, I can't hear you.
It's 90 instead of
It's
9.
not. No. 0.3 squared. It's
0.3 squared is equal to 0.09, and 100 times 0.09 is 9. Yeah?
It shows something else.
I got 9.
I contend that it is right. Okay? Now, it turns out that this is going to be 0.01, and 100 times that is 1 joule. So now I've got 9 joules plus 1/2 times 4. You know, let's just get rid of the units, make this simpler. 9 is equal to 1/2 times 4, V squared, plus 1. So I subtract 1 from both sides. 8 is equal to 1/2 4 V squared. And so that gives me 4 is equal to V squared, or V is equal to 2 meters per second. Now actually, the velocity could be positive or negative 2 meters per second, but we're asked to find the speed. The speed is the magnitude of the velocity. It's always a positive quantity. It's what you see on the speedometer. So the answer would be 2 meters per second. Is that right? Mm-hmm. Okay. Let's use our clickers and solve this problem and give me your answer.
Write the formula on the boards.
We all get it right, we go to Disney World.
Hold on. Hold on, what do we have? Force. So F equals 20. It elongates. So when it elongates, that means that it's delta It's gotta be static.
Okay, in the interest of time, if you haven't voted yet, please do so and get your clicker points. Okay, last call. The answer is B. Good job. There's two ways to find a spring constant. The static way, you pull on it and you see how much it stretches. The dynamic way, you bounce a mouse on it and you find the period, and the period is going to tell you what the spring constant is. Well, in this case, we need to find the period, and so we can't use the dynamic method. We are told that if we pull on this spring with a force of 20 newtons, that it's going to stretch by 0.2 meters. Now that means my K value is going to be 100 newtons for each meter. Now if I come over here and find the period, that's going to be 2 pi times the square root of the mass is 4, and the spring constant is 100. Well, that's going to be 2 pi is 6.28. Square root of 4 is 2. The square root of 100 is 10. It's almost like I cooked these numbers, right? Now this is going to give me 12.6 over 10, or 1.26 seconds, which is 1.3. Okay, let's try a trivial one. Now, folks, this was an exam problem that caused trouble. It was the easiest question on the exam. It caused trouble because I used that word cycle and people got confused. A periodic wave on a string is observed to have exactly 2 cycles in a 3-meter section of the string. What do you mean cycle? Bicycle, tricycle, unicycle? A cycle is a repetition. If you have a cycle in time, that's the period. If you have a cycle in distance, that's the wavelength. Now, I firmly believe that if I had said there are exactly 2 wavelengths in every 3-meter section of the string, everyone would have gotten it right on the exam. So that's what I'm telling you. There are 2 wavelengths, okay? 1, 2, and that's 3 meters. What's the wavelength?
1.5.
1.5. Now, if you know that the speed of the wave is 20 meters, find the frequency. It's not hard. It's not hard. Oh, and when you do, use your clicker. Okay. Folks, this was intended to be a gimme problem. The most important equation with waves is the wave equation. And this was just a plug and chug to see if you could use that equation. If the speed is 20 meters per second and the wavelength is 1.5 meters, then the frequency is 13 hertz. Everyone choose C. Okay. Oh, we would have gone to Disney World. Dang it. Okay. People, we have 1.5 minutes. I'll help you get more points on the exam. Okay? You have a tube. This tube sustains standing waves at 500, 700, 900 hertz, but not at 600 and 800. The question is, what is the fundamental frequency of the tube, and is it open at both ends or closed at one end? The way you solve these problems is you use the fact that neighboring harmonics are always separated by the same number of hertz. In this case, 200. So what you do is you keep on working down towards 0 by subtracting off 200. But you don't go to 0 because that's not an oscillation. And you never go negative because there's no negative frequencies. The lowest frequency that you find is F1. And then you ask yourself, is this F2 or F3? Well, it's 3 times F1, so it must be F3. This is 5 times F1, so it must be F5. This tube, is it open at both ends or closed at one end? It's got to be closed at one end so that I've got a node and an antinode. The even harmonics are missing. Have a good weekend, people.